going to get started with Peter Haynes from Cambridge, who's going to tell us about ocean jets.
Okay, thank you, Marie-Louise and Bruce, for giving me the chance to talk. My original title was kind of somewhat vague about, and this is the title that I've kind of focused on. And seeing it here in kind of large letters sort of makes it, was it the best choice? I mean, I'm going to talk about certain sorts of ocean jets, right? And then also, I'm a theoretician, I'm not an oceanographer. And so the kind of, the quest here is, what does one need to include in the simplest possible model to capture the kind of phenomena that you may see in the ocean? First of all, I'm going to motivate this by talking about work that other people have done, ocean jets in models and observations. And then I'm going to go to the kind of simplest possible model, 2D flow on a beta plane, the stochastic forcing, and talk a bit about the difference between the doubly periodic case that is being studied a lot, and the case with rigid boundaries, X boundaries, which is kind of from the theoretician's point of view, is the ocean-like case. Talk a bit about Basin modes and nonlinear Western boundary dynamics, and then at the end I'll talk about what happens if one inhibits Basin modes. Okay, so the kind of context for this is, 20 years ago, people started to get very excited about the fact they saw jets in unexpected places in ocean models, and to some extent in observations, right? So, this is an example from a paper by Kelvin Richards. This is from a sort of, at that time, state-of-the-art ocean model. They're looking at the zonal velocity. This is actually averaged over about 3 years. What you can see are kind of jet structures, okay? And you see them in, you see some jets in some places where you expect. In the ACC, you can see kind of complicated braided jet structures here. But I think what was unexpected was the fact that you saw what seemed to be jets in many other parts of the ocean as well. Particularly in the low latitudes, but also in mid latitudes as well. And then also there's evidence in observational fields. The picture on the left is from, I've taken that from the excellent Gulper and Reed book, which and that's showing the kind of jet structure emerging from satellite altimetry. And so then the kind of conventional wisdom to some extent on these jets is that to a large extent they're what are called latent jets. You can't see them in the kind of instantaneous flow fields. Many of them emerge only when you take time average. Okay, so the term, Pavel Berloff and others have used the term latent jets. And then, and also there have been studies of transport effects, transport in these flows. And transport is often found to be anisotropic, but in many cases it's found to be that that's an anisotropy in the eddies, not so much in the transport effects of the mean flow. I'm kind of mentioning that because some of you may be kind of thinking about these things. That's sort of relevant. Okay, now a few years ago I spent some time in Toulouse at Lagos, and was interested to hear about lots of work going on there. And one particular sort of very interesting sort of set of work was being done by Sophie Cravat and others. This is building on observational work that I think has been going on in oceanography for many years. I think the point about this work was it was perhaps making use of a longer term, more coherent data set. And so in this paper, Cravat et al. 2017, they were using two different data sources to show that there were persistent jets in the low latitude ocean. So we're now looking from 15 south to 15 north. We're seeing jets at different levels. This is a kind of different potential density ranges. This corresponds to something between 110 to 450, depending where you are, 400 to 600 meters and kilometer, right? So you're seeing these strong zonal structures appearing in these observations. These are constructed from Argo data, so it's a combination of temperature and salinity being used to calculate geostrophic velocities together with some of the velocity information from the floats, which is providing a kind of reference point. And then one thing that interests me was that the vertical structure of these jets. So again, this is vertical structure based on the Argo information, and then this is vertical structure based on acoustic Doppler current profiling. And so what you can see is, so this is now latitude here, depth. You can see these jets, they're extending into the subthermocline ocean. You can see a kind of regular latitudinal structure. You can see subtle changes in the vertical structure, right? So that if you go to away from the equator, these jets tend to be kind of simple, deep. If you go closer to the equator, you can see some kind of subtleties here in the vertical structure. And then if you look carefully, you can see strong differences here on the equator itself, perhaps not surprisingly, because there the Argo information is going to give you, be very adequate in terms of velocity information. And then this was a nice sort of schematic, which was included in a Menescuin paper a couple of years later. So the picture is, there's this kind of wealth of different currents in the low latitude ocean. There's a set here which people have thought about for a long time as equatorial deep jets. I mean, these are kind of, to me, these are very different from everything else, right? These are people like Lenoir spend a lot of time studying these jets. They're kind of stacked in the vertical. There's evidence for role of particular equatorial waves, possibly a role for inertial instability. Then go away from the equator again. We've got this more complicated vertical structure near the equator, and then deep jets further away from the equator. And Menescuin applied a kind of naming convention to these jets. I won't go into the naming convention, but basically there are what they call intermediate currents and subsurface currents closer to the thermocline. Okay, now then, what I thought was particularly interesting was some subsequent work by Audrey Delpech and others, where they looked at the tracer structure. So this is now, the acoustic Doppler current velocities here, and then this is the structure in oxygen, and it's shown in kind of two ways. This is a kind of shallower structure going from about 200 to 600 meters, and then this is a kind of deeper structure. And let's focus on this picture, for example. So here you've got an strong eastward jet. You can see that if you look at the oxygen here, you've got sharp gradients coincident with the strong eastward jet. And then if you look in this deeper picture, again, you can see the sharp horizontal gradients, extending quite, down to 1,000 kilometers or so, sorry, 1,000 meters or so. So what you're seeing here is kind of what, many of us were kind of sort of predisposed to think of when you're thinking about structures of jets and tracer transport. But it seems as though that the eastward jets are kind of acting as some kind of barrier which inhibits mixing, and that between the jets, inverted commas, right, then you have a rather flat tracer structure in latitude. And this is what people talk about as a staircase. In this context, it's a staircase in the horizontal, right, rather than the staircase in the vertical. That's been a big kind of theme of this workshop. So to me, this is all kind of interesting. How does this work? If you're interested, I recommend the Delpech et al. Paper. This picture is, making the point that these staircase structures seem to be coherent in longitude as you go across the basin, and the argument there is that actually they're also, can be observed over a period of about 20 years. So the questions that you might be motivated by, if from these results. Now, the first point actually is that, if we think about latent jets, these are jets which are existing in this context of you can't see the jets in the instantaneous flow, but you can see them if you take long enough time averages. we wouldn't really expect those to be associated with strong tracer structure, I think, right? So one question is a kind of slight mystery about if some of these jets are latent, why are they associated with strong tracer structure? Another question is what's driving them? Another question is what's is controlling this vertical structure, right? Now I'm going to make the simplifying assumption that I'm going to ignore these, what's on the equator. I'm going to focus on the structure which is away from the equator, and then I'm going to imagine that this is sort of essentially described by some kind of quasi-geostrophic theory, that we don't have to kind of bring in the details of sort of deep equatorial dynamics here. Now, I wouldn't want you, these are all interesting questions, right? And I wouldn't want you to think that in 20 minutes' time I'll have answered them. Okay, actually what I'm going to now do is kind of go into the details of idealized theoretical models and sort of ask, well, I mean, I've said, well, I'm sort of imagining that quasi-geostrophic 2D type mechanisms are relevant here. If I start to go to models which include those mechanisms, how exactly are they working, what's going on. So, starting point is the kind of the workhorse of two-dimensional vorticity equation on a beta plane. Essential ingredients. Stochastic forcing. You've got to, with single layer system, you've got to make something happen. I'm going to assume that, at this stage, I'm going to consider models where the energy is being put in at small scales. You have some kind of damping which brings the system into equilibration. And of course, a lot of the previous work on this has considered the kind of doubly periodic case. This is supposed to be a graphical description of doubly periodic. You've got a box that's just repeated. There are no rigid boundaries. If we're going to go to the ocean, then we might say, well, the vital point is we've got continental boundaries. So let's consider a system which has rigid boundaries here, but we'll get to be as simple as possible. We'll make it periodic in this direction. Okay. And again, if you look at Galpin and Reed, I mean, there's some discussion of this. Some statement is that this is there's been much less work on this kind of configuration than there has on this. Of course, I mean, but there has been important previous work by people like Pavel Berloff and Nadiga, Strauss, Joe Lacache, etc. And there's some good reviews of this in the Galpin and Reed book. Now, there are some standard ideas kicking around in these kind of models, right? Sets of scales. I mean, there's this idea of the Rhine scale, which might be a scale for the separation of the jets, given by a square root of velocity over beta. Of course, the key question is, what is the velocity exactly? The idea is you're putting energy in at small scales. At small scales, you're seeing essentially an upscale energy cascade, as described by two-dimensional turbulence. At some point, the system feels beta, and that's given by this scale here. And so then this idea of going from two-dimensional turbulence to some kind of wave motion, right? That's the scale at which that transition happens. Then, if you use the idea of the energy balance setting this, the U here, then you can estimate a Rhine scale through this thing here, and then a key kind of parameter is the ratio of the Rhine scale to the scale at which the system feels the wave motion, and that's what's called the xenostrophy. Okay, and it ends up looking like this in terms of the parameters: the energy input rate, the beta gradient, and mu, which is the damping. Okay. So the kind of convention, the picture that we get from doubly periodic systems is that you have large R beta, you have strong jets. If you have small R beta, you get very weak jets, possibly no jets, right? I mean, I'm just showing this as a kind of reference point. This is a kind of typical instantaneous zonal velocity that you see, function of x and y. I mean, here we're in a strong jet regime. You can see the jet in the instantaneous flow, right? As we work down here, the jets, if they exist, become more and more imperceptible in the instantaneous flow. And this is pictures of the zonal mean flow against time. Here you've got a strong jet which is meandering a little. Here you've got more strongly meandering jets. Here you may or may not have jets. Good question about this. Now then, if you do this exercise of taking the time average, then you can kind of see that in a regime here where the jets aren't obvious in the instantaneous flow, you can see the jets in tri-average. This is actually a picture showing different averaging times, right? I should emphasize, this is work which being done with Xue Zhan, and these pictures are being been provided by him, so I much appreciate that. So you can see that as you go to longer averaging time, the jets persist. Here again, you can see as you go to longer averaging time, you've got persistent jets. They're weak, right? Because after all, you're averaging a fluctuating signal, and there may or may not be jets in the time average here. Okay, now then, this is a kind of standard result. If we go to the rigid X boundary case, so we simply stick in rigid boundaries, then in the instantaneous flow, we see it's very difficult to distinguish any kind of jet-like behavior. Okay. On the other hand, if we look at the time mean, this is the time mean flow averaged over some suitably long time, then you can see strong jet structure. Okay. Of course, the key point here is that the scales here, right? That the color scale here is enormously magnified relative to that in the instantaneous flow. When you do the time averaging, you're seeing weak, but nonetheless rather coherent jets. This incidentally is the kind of zonal mean flow as a function of time here. Difficult to see anything there. And this is the zonal mean flow averaged over different time scales. So you can see that out here you're seeing the time mean jets, but they're significantly reduced in amplitude relative to the instantaneous flow. Okay, so all of this has been shown by others. I found the literature sometimes a little bit confusing, but essentially we're all agreed that in this geometry, we've got high down steady flow fields. We can see jets in the time mean. So what's going on? Well, the key ingredient of these flows is the fact that you've got wave modes as a result of the meridional boundaries, right? You have what are called Basin modes, which are basically superposition of Rossby waves, one eastward propagating, one westward propagating, in terms of group speed, that satisfy the boundary conditions. And you get a simple dispersion relation and prediction of the frequencies of the Basin modes. And what you see is that the flow, the time-dependent flow, is to some extent dominated by Basin modes, right? So my interpretation of what's happening here is that, again, you're starting with energy input at small scales, two-dimensional turbulent inverse cascade is pushing your energy upscale. At some point, the system feels the Rossby wave ingredient, and what you've essentially got is a stochastic forcing for the Basin modes, right? So what we're seeing here are stochastically forced Basin modes. And this is just energy as a function, or activity as a function of frequency here. The dashed lines are the Basin mode frequencies. Here you can see good correspondence between what you measure and the Basin mode frequencies. Your increased beta, you again get good correspondence, but you see a different set of Basin mode frequencies are occupied. That's essentially because this scale, the ellipsilon scale, depends on beta. So if you have beta larger, then you won't get to such a large scale before you excite the Basin modes, right? So, and you can estimate the scaling of the frequency. We haven't actually tested this, but the frequency is likely to go like beta to the 2/5. And so, of course, then if you look at the velocity field, you see this is the instantaneous u velocity in case of two different beta. then what you see are fluctuations on the timescales of the Basin mode, right? You don't see strong, coherent zonal jets. Now, actually, one interpretation of all this, one of the papers on this topic is that actually, when you take the time mean, you are essentially taking the time mean of a stochastically forced wave, and so over any finite time, you're seeing a non-zero average, right? So it could be that the time mean flow is essentially simply the result of taking the finite time average of stochastically forced waves. So let's examine that. One could do what I call a Basin mode spectral decomposition, although this is a slightly misleading term. I mean, what one's doing here is one's taking the spatial functions corresponding to the Basin modes and using those as a basis set for spatial variation, right? And so this is the kind of energy spectrum in terms of Basin modes, numbered in a suitable way. Corresponding Fourier energy spectrum is more spread because the Basin mode doesn't consist of a single Fourier mode. And if you take these examples, I mean, here we're looking at a particular Basin mode, and we look at the variation of the coefficient of that Basin mode, what we see are nice regular oscillations at the expected frequency, right? So there's no doubt here that when we examine these sorts of features, what we're seeing are essentially Basin modes, stochastically forced. If you looked over a long time, you'd see shifts in phase and things. Now let's try and apply that to the time mean flow, right? So the Basin mode spectrum for the time mean flow, there's activity up here. This is what it looks like. If we take this Basin mode, what does the time variation look like? Well, it doesn't look like Basin mode oscillation, right? It's a sort of stochastic jumble. If you look in frequency, then you can see a whole set of frequencies here which are significantly lower than the Basin mode frequency, right? So I would say that the time mean jets that you're seeing here are not simply a finite time average of a stochastic Basin mode. Now, there are some interesting Western boundary effects going on. I'm going to stick my neck out and show a movie. Again, created by Shiwei Jiang. This is the U field. You can see in the U field that the dominant Rossby wave, right, is the one which has group propagation to the west, and you can see something a bit different happening near the western boundary. If you look at the vorticity field, then you can see that the western boundary, you've got all these this vortex structure. Again, I mean, I think in terms of textbook terms, many of us would recognise this. You've got long Rossby waves propagating to the western boundary. They're in some sense trying to be reflected as short Rossby waves. The nonlinearity is stronger. You're generating a strongly nonlinear effect. Right. Now the question is, can I get out of this slide? No? Okay, right. So the interpretation here actually is that the structure you see in the time mean flow is not so much the average of a stochastically forced Basin mode, it's more being controlled by this nonlinear flow in the western boundary. If you look at the time behavior of U averaged over the whole domain, you see that it's the time variation is dominated by the Basin mode frequency. If you simply go and look in the western boundary region, you see that the time scales are much longer here, right? So the kind of vortex dynamics that's taking place in the western boundary region is on a much slower time scale than the Basin modes themselves, and this kind of nicely corresponds here to the structure here to the structure you're seeing in the time mean flow, right? So I'd say that this long time mean flow is being to some extent controlled by the nonlinearity in the western boundary current. But of course, this time mean flow is very weak, right? So to some extent, it's of academic interest. So where we've got to, well, that's my kind of summary so far. Now the key point is here, I mean, you can argue that there are sort of two different effects of boundaries, right? One effect of the boundaries is that you've got Basin modes. Another effect of the boundaries is that you don't have this kind of possibility of recirculation that you do in doubly periodic flow, right? I mean, doubly periodic simulations, you've got jets coming in one side of the domain, going out the other, right? With the ocean boundaries, you don't have that, right? To me, both of those are interesting. Let's see if we can get rid of the Basin modes and simply look at the effect of the boundary conditions on the kind of longer time flow. And now, you have to admit, right, well, why is it that ocean, if we go back to the Cravattatel, observations, I mean, why aren't those jets being disrupted by Basin modes? I'm not sure, right? Therefore, let's kind of find an escape route. Let's put something into our model which is going to inhibit the Basin modes. Let's imagine we've got some kind of strong damping region and a weak damping region. We imagine that the existence of the strong damping region is going to prevent the kind of reflection backwards and forwards of the Rossby waves, and therefore inhibit the Basin modes. One can kind of come up with a sort of modified theory for the turbulence that's happening in this undamped region. Basically, one has to consider the possibility, I mean, energy will be generated in this region and propagating out, right? So in some sense, in the doubly periodic world, what's doing the job of dissipation is, you have a dissipation which is dissipating energy. In this world, you're forcing this system, but then it's equilibrating energy by propagating energy out of the system. Okay, so we're going to end up with a kind of corresponding definition of the R beta. Bottom line is, well, in this case, you can get non-latent jets, right? I'll cut to the last picture. So here we've got rigid boundaries, and we've gone to a long domain, right? Because actually you can get larger values of R beta in a long domain. And then these are time snapshots. And what you can see is that in these cases, the jets are not latent in some vague sense, right? They're quite visible. And so the existence of boundaries here and here, right, does not in itself inhibit the formation of the jets, right? It's not essential for these jets to be able to recirculate. What inhibited the jets in the first case I talked about was this generation of Basin modes. So where we've got to, basically, these observations, in particular the tracer observations, right? So, they've shown a tracer structure. They suggest what I would call non-latent jets. If you go to the simplest model you can think of, well, then you get a flow which is dominated by Basin modes, and that's a mechanism for meaning that the jets are latent. They can only be observed in the time averages. If we inhibit the Basin modes, then we can now achieve jets in a domain which is confined. Okay, the confinement by itself is not a problem. And then, of course, we can go back to the real ocean, or might be people here who can comment on this. I mean, first question is, why are Basin modes so dominant in the simplified model, but perhaps not in the real ocean? And of course, there are also these interesting questions about the mechanism for forcing and for the vertical structure, which still need addressing. I'll stop there.
Thanks, Peter.
So, two kind of related questions. If I understood your message, would it be fair to say that from the point of view of modeling, you could dispense with everything up to the crossover scale with the waves and just treat it as a forcing, and then do the problem as in terms of the dynamic, the interaction of the Basin modes?
I wouldn't say that myself necessarily, but what I would say is that what I believe is happening in this case is that energy is feeding up to a scale where you feel the wave dynamics and providing an effective stochastic forcing for the basin modes.
I mean, that's the obvious implication of what you're saying.
Well, I didn't have an agenda, that was simply
Sort of related to that, how do we understand, say, the basic ideas of jet formation in this ensemble of basin modes, like the Rhines mechanism and all these other goodies that we've heard about since
Well, I mean, the bottom line is that the basin modes you see as a consequence of these rigid boundaries, right? Now, of course, there are we could now go to the sort of theories for jet formation, right? And ask why don't they work, right? And I mean, I haven't had time to go into that here. I mean, but you can think of different aspects of theories for jet formation. I mean, one is about the kind of anisotropy of the spectrum and the fact that different parts of the spectral space are inaccessible. You can think about the whole idea of condensation, that you're kind of naturally feeding energy to a large scale and achieving kind of quasi-steady, quasi-unforced structures. Each of those you can sort of think about. You can think about the implications of the boundaries for those things, right?
Sure.
So that's possible, but because there's a bunch of theories, none of which are kind of mutually exclusive. Sometimes they're almost more a statement of belief than a basis for testing hypotheses. I haven't tried to comment on that, but yeah. But for example, condensation one can look at in the context of how condensation changes as you add beta.
So, of course, it's important to start simple like you've done in your model, but the real ocean, of course, doesn't have simple boundaries.
Indeed, that's right.
So the question is, do basin modes even exist in anything but simple rectangular?
Well, I mean, basin modes have been observed, right? I mean, that particularly in the equatorial ocean, people have written papers where they have observed basin modes, right?
Okay.
So,
but are they mathematically definable for a problem like you're doing when you have maybe irregular or non-straight boundaries?
well, I think that, that's an interesting question, right? And that's what one needs to think of, and it would be very interesting to know if others here have thought about that, right? Because it would be very easy for me to say, my damping region is a representation of irregular coastlines, right? But I wouldn't want to do that before understanding whether that's really true.
Okay, let's do one more.
So getting back to your observation where you had the tracer of oxygen, and you were saying it's not clear how the tracers can link into the dynamics of the jets, it wasn't clear to me that your model would address why you might have a linking between the tracers and the jet dynamics.
Well, sorry, I mean, in thinking about the jet problem, right, if one thinks about the problem of beta plane jets in various contexts, then it's natural to associate the dynamic organization with also an organization in transport, right? So there's quite a few papers have been written about how tracer structure relates to the structure of the jets, etc.
It's just that the Rossby waves wouldn't have a mass transport associated with them.
We're thinking more about sort of mixing in the latitudinal direction, whether or not mixing can occur, whether the presence of jets inhibits mixing in that sense.
Okay.
But if one looks, the sense of the work that's been done on that is that one requires a certain strength of jets to act as a barrier to transport, to promote the formation of mixed regions versus barriers, etc. Right? If the jets were kind of purely latent and existing in a very weak sense in a time average, it's not really clear to me that they give you that ingredient. So that's why it seems to me it's interesting to kind of explore what is, it could be that the jets which are described, which indicate the strong tracer structures are not latent. And then the question would be, well, why are they, where's the kind of disconnect, as David said, between the simplest model and the non-latent jets, right? I mean, what does one need to include or exclude to go from a world where jets are latent and highly disrupted by basin modes to a world where they're more coherent?
All right, one more question.
Okay, can I just ask you, you've clearly got a small parameter in your problem. Is it EZ over E?
Sorry, that was, yeah, that was simply a measure of the amount of energy in the zonal mean, in the x-average flow versus in the, that was a diagnostic.
Right, but what is the small parameter? Because you've got waves and then you've got a mean flow which looks like it's quadratic. I suppose.
Well, I mean, I think the issue, yeah, the issue is what it, perhaps there isn't a small parameter necessarily here. I mean, if you think about, for example, the condensation type limit, where you have a large-scale structure which is strong, and your superposed eddy field which is weak, right? Well, then you have a, I mean, it's weak in the sense that you've put a lot of energy into the large-scale structure, then you can see a small parameter, right? But in this problem, it's not clear to me what the small parameter is, right?
Because your mean flows are like 10 to the minus 4, and your other measures are 10 to the minus 2.
Well, I mean, yeah, one could ask questions like, you know, what is the weak mean flow that exists in this strong wave field, right? But to some extent, I don't know, perhaps I'm not particularly motivated by that because it's not really clear to me what this weak mean flow would do, actually. Yeah, one could do a theory for a weak mean flow in a strong wave field, but it wouldn't really get to the problem that I was interested in.
Excellent. Thank you, Peter.